Hello everyone. In this video, I'm going to demonstrate the fetch, decode and write back, and execute and PC update stages of y86 sequential processor. But we will focus on the execution stage because this is the recent module we just added in this design. So it is taking two operands, ALU-A and B, and its function code, ALU-fun. And then these inputs are generated by three conditional module, ALU-A, B, and fun. And it outputs the outcome of this computation or operation to val E, and it also outputs condition code. And condition codes will be stored in the CC module if setCC module generates signal 1. And this setCC module will generate signal 1 if current instruction is arithmetic or logical instruction. Actually, if I code equals to 6, then this module outputs signal 1. And then we have a cond module here, and it will generate a 1-bit signal for jump and conditional move instruction to make a decision to jump or not, or move or not. Okay, so again, we are using same program, which is array sum, but we will execute some more instructions here because our process is almost complete except memory module. So we will stop until when we see the instruction we cannot execute because we don't have memory instruction. Okay, let's get started. And here, I'm in the previous demo, I executed 10 cycles. So actually, I ticked 10 times every time, but in this case, I'm going to execute. I'm going to tick entire number of cycles for one instruction, which is 20 ticks or 20 cycles. And then we'll see the outputs of some programmer visible states, or some internal values. Okay, let's execute first instruction. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we finished executing one instruction. What did we execute? We execute IR move instruction. We put the label stack to the RSP. And what is label stack? So it is actually a label. Label 200. Okay, memory address 200. Okay, so then we expect to see the value 200 in register RSP. Okay, yeah, so 200 is stored in RSP. So first instruction finished. Okay, let's run second instruction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we finished second instruction. So which is call main. So it jumps to main label, which is at memory address 38, and then we push the next return address, which is address 13, okay, to the top of the stack. And then we reduce the uh, and then we just reduce RSP by -8 because the stack starts from the higher memory address and then grow down to the lower memory address. So since we pushed one return address, we should the stack should grow down to the memory. So then we expect so RSP to be reduced by -8, and then we expect to see the next PC value would be 38. Okay, let's see. Okay, so next PC is 38 is correct, and then the updated RSP is okay. Yeah, 200 -8 1F8. Okay, it is correct. But we cannot see the stored return address in the memory because we don't have memory. So we cannot actually execute return instruction in this with this processor. Okay, so then we'll execute instruction at memory address 38, which is our move instruction. So let's execute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So let's go back to this instruction and try to run ourselves. Okay, it moves the array value to the RDI. And what is array label, which is memory address 18. So then we expect to see register value RDI with 18. And then next instruction would be 42. Okay, let's go there. So RDI is 18, correct? Yes, 18. And then next instruction address is 42. 42. Yes, it is correct. Okay, then let's move and then execute next instruction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Then what is the next instruction, which is RI move Q and 4 to RSI. So this is simple instruction. So we will see RSI register with 4, and the next instruction address will be 4C. Okay, next instruction is 4C. Next instruction address is 4C, and then the value of RSI is 4. Okay, but by the way, please note that all other visible state shouldn't be changed. Like some RAX, we never touched this register, then it shouldn't be changed all the time. Okay, good. The next instruction is another core instruction. Okay, let's execute first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then let's go back. And then again, we expect to see the next instruction address would be 5, 6. Okay, it is correct, 5, 6. And then we'll see the reduced RSP value by 8. And then actually we will store the return address 55 to the memory register at the top at the memory at the top of the RSP stack. But since we don't have a memory data instruction, we just check reduced RSP here. Okay, RSP was actually 1F8 before, but it is reduced to 1F0. Okay, it is correct. Okay, then let's move to the next instruction, which is at memory address 56, and it is again IR move Q 8 to R8. So after this instruction execution, we'll see value 8 in the R8 register. Let's see. 1, 2, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay, in the register 8, we see the number 8 here. And the next instruction address is 60, which is correct, 60 here. Okay. Next instruction is what? Next instruction is, yeah, XOR Q instruction. And then we'll see the RAX with zero value in RAX because it is XOR instruction with same registers. Then we'll it is kind of clearing the RAX value. But since the RAX is already 0, so we won't see any changes. So let's run it. Okay, 9. Okay. So no changes in RAX, but the next instruction address is 6A, which is 6A. Where is it? Oh, sorry. We executed the previous instruction, which is IR move Q 1 to R9. So we got R9 like one value in R9. Okay. So it's my bad. Then it is time to execute XOR. So let's quickly execute this instruction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. Then no changes in RAX, but changes in next instruction, which is 6C. Okay. And next instruction is AND Q instruction with RSI and RSI. Okay. It is actually checking whether what's that? This RSI makes condition code 0 or not. Right? Because we are going to use a jump instruction in the next. Sorry, it is nothing to do with that. Okay, I forgot the context, but let's just run it. We don't have to follow the, we don't have to have a context. We just execute as a machine. So what we expect from this instruction execution is going to have a same value in the RSA because it is AND with same registers, and then some updates in the CC value because it is what's that? Logical operation, and then we will see the updated PC value here. Run it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, RSI didn't change. So previous value was 4, so it's not changed. But CC value now is what? So condition code is here, so 0, 0, 0. Okay. And then next, is it correct? I think so. Yeah, it's correct. It's not, it's positive, it's not 0. Sorry, it is not 0, and then it's not overflow. So we got all 0 values. Okay. The next instruction address is 6E. And then we are at 6E, which is jump instruction. Okay, then let's run this instruction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's see what we executed and what is the expected output. So since it is unconditional jump, we'll just jump to test. Okay, so nothing will be changed, but next instruction would be 8, 7. Okay, so next instruction is 8, 7 here. That's good. And then yeah, we just jump to test, but here we have a JNE instruction, the jump not equals to loop instruction. So then what was the last instruction that changes the condition code? It was, yes, the AND operation with RSI. So this instruction will, make the terminal condition of this entire loop. So if RIS is making a zero flag set, then it will not jump to the loop, and then it will just fall down, and then return. Okay, so let's run this test instruction, and we expect to update PC value with loop address loop, which is 7, 7. So let's run it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But in this case, I'll stop after one cycle before we finish this execution. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Then let's see the output. Condition code. Output of cond module, so which is 1. And then it indicates that we should jump to the label, because the result of condition, the evaluation of jump condition is 1. So which means we should take which value? So we should select yes, I think this val C, which is the the address to jump. Yeah. So which is 8, 7. So sorry, this is 7, 7. So this is not the actual value. Sorry, is it? Let me correct correctly. Yes, I think this is 7, 7, and this is actually jump address. Yeah, so my bad. It is correct. So when I tick once more, so now we have one more side ticks to go. So when I click once more, then so PC value will have the 7, 7 value. So now it is at 7. Okay, let's run one more tick. Okay, good. Then we got 7, 7 for the next instruction address, which means it jumps to loop. Okay. And then here, okay, we are almost there. So let me run the next instruction, which is MR move Q instruction. Okay. But the thing is, we don't have data memory, so we cannot actually read the data from the memory and then put it to the R10 instruction. So we can stop here. So once we reach here and we don't see any error, then okay, we are good with this execute stage. Okay. So in the this is it for the demonstration of extrusion stage. And in the next video, I'm going to talk about memory, data memory, so memory stage. Thank you.